Well, I often like to say hot balls of gas. Everybody knows stars are made of hot balls of gas. I've always wanted to say that in an audience where that's really true. Are you saying this is a little too loud? Okay. Pull it away a little bit. Going to be talking about planets migrating into stars. And that's why I talk about hot balls of gas. Going to be emphasizing the shortest period distribution and talking about star-planet metallicity correlations. If we learn one thing from learning about many different planetary systems, we learn that planets scatter off each other. But of course, as Rosemary pointed out, they don't have to bang on each other directly to do so. Going to talk about two different debates. One debate is the occurrence distribution. Why are there so many of the shortest period giant planets? And the part of that debate that I want to emphasize is why are there more hot Jupiters than hot Neptunes? The second debate would be this planet metallicity correlation. And since 2012, I and some others have found some correlations between other planet orbit parameters and wonder why we have those. So, in the shortest period planet distribution, the question that I want to emphasize are these shortest period giant planets, are they there because they remained there due to not tidally migrating in? Have they remained there since formation due to weak tidal migration? Or I'm going to promote that it's reasonable to consider that they've been flowing in there. And as I've been pounding in on this point since 2012, I see more and more papers coming out considering that there could be a flow or a current of planets going inwards. And the main point that I have is that the numbers are not too large. These shortest period planets are in fact quite rare. And so a flow of planets, you don't have to reduce the more distant current distribution or the planet occurrence by much to supply this. Okay, so also with regards to why are there fewer Neptunes, why is there the Neptune desert? I've been promoting the idea that there's more giant planets migrating inwards. This could have to do with the three-day pilot, but maybe the three-day pilot of giant planets is actually supplying planets going inward. Of course, Mazza et al. In 2005, they said that maybe the Neptunes are evaporating. Well, if so, this would provide a wonderful opportunity to study the rock planet, the rock gas transition. We've seen this plot several times, that there's more giant planets. I think we've seen that quite a few times. Here I show, we've often seen the period versus star mass, but if you look at the lifetime versus star mass, you notice that the shortest lifetimes, according to the equations we've used, and that is if you consider that Q is constant across all stellar masses, then you actually see a decrease in lifetimes with stellar mass. Here's WASP 18 having the shortest lifetime, the biggest surprise. Perhaps this indicates that the tidal dissipation is actually weaker for these more massive stars, which would make sense given that they have a smaller convective zone. Though, of course, you have to remember that there's more younger stars here because they simply don't last as long. Their lifetimes are shorter. I've used the Howard distribution because he was so careful in making his cuts. Andrew Howard, he took, to make this distribution for the three different, he took three different radii distributions. This is the large radius, this is the medium radius, and this is the smaller radius of planets. And you notice that when you do a fit, and I don't really care about ignoring all these details out here, since I'm mostly interested here, but you notice that there's more Neptunes everywhere except the closest distance. Now in this function, I take beta plus gamma to be alpha, that this slope is really more alpha when you take the limit of this function in the shortest period. And from this, I'm able to operate on it with the tidal migration equations and derive a rate of planet flow. And you'll notice that if you have a power index of 13/3, that the 13/3 is an indication that these planets are flowing in. And so I've made plots for different power indices for periods of different amount of years, and here I've done it for a tidal migration strength of q to the 7, tidal dissipation constant of q to the 7. And you can see that thinking Eureka, for both the giant and the medium planet distribution, the Howard fit is very close to having the same power index. Of course, this is based on very small statistics. The error bars are really huge. And so this very well could just be coincidental. But this is a reason I say that looking for more planets, having K2 look at many different fields, having more ground-based surveys, and very importantly, finding out what the denominators are for how many, when we say we find planets, we want to know what fraction of the total. And that is a difficult problem to evaluate with the ground-based surveys. But we need to know what the total number of stars each planet represents, total number of stars without planets, so that we can really see if these planets are going in as I would like to think so. So for a reasonable age distribution, I find that well, let's see, I agree with some of the work by Pinna et al. And others that if you don't have new planets coming in over here, the giant planet distribution, you want a very weak tidal distribution, or very high Q, remembering that Q goes inversely as the strength of the tidal distribution. But looking at the Neptunes, it fits better with a weaker tidal dissipation. And so I'm saying you could just account for the difference with the flow. And here with the fit, and here with the actual Kepler planets, I've modeled that, okay, with different strengths, this is the strong tidal dissipation, and without a flow, this is not reasonable to have this strong of tidal dissipation. You want to have something weak like this, so that we don't consider right now to be a special time in the universe that we've found so many planets. But I'm saying that these, in fact, could be reasonable if you fill in this gap, if you fill in the difference. It only takes on less than 1 planet per 1,000 stars per gigayear, 10 to the minus 12 planets per star per year, to fill in that gap. Over a 10 gigayear lifetime, that only reduces planet occurrence by 1%. That's reasonable. So even though we don't know whether having the data and the theory power index being the same, whether that's coincidence or whether that's real. Well, this is going to be something, a theoretical framework to hang future results on. And I've also here derived how fast, as a function of age, how fast this power index moves out, how fast the fall off moves out, and then where the fall off will be as a function of time. And what really determines how fast it moves out is the difference in power index of the fall off region and further out. And of course, figure that alpha is probably around 13/3. Let's see, somehow I went to the very end. Okay, the quickest way that we're going to find what the strength of time dissipation is, we're going to see some time shifts. And within 10 years, they could be over 100 seconds. This is for 10 to the 6th. So if time migration is 10 to the 7th, that's kind of where the debate is going, and I'm quoting maybe it's stronger than 10 to the 7th. It might only be 1/10 of this, but still, we probably with better measurements will be able to look for a time shift. Now WASP 18 is high up here, but perhaps WASP 19 and WASP 43 are going to probe different stellar masses, and that's very important if the tidal migration strength is a function of stellar mass. Now quickly on the debate number 2 is that from 2002, notice that there is a correlation between metallicity and orbital eccentricity. And Rebecca Nelson, she found this not too long after I did, and she figured that you could have more crowded planet formation if you had higher metallicity in the beginning. I figured that when I was looking for a sign of pollution, I think, well, that these two explanations could in fact be complementary. And I found some work in 2002 that also Murray and Chaboyer also looked at the possibility of, go to the next slide. The possibility of whole planet pollution. So, found a lot of signs that the planet population for iron-rich stars is significantly different than for iron-poor stars. Let's see, this just shows the significance, and you can ask me afterwards that the significance is very strong here. If you look at the orbital eccentricity as a function of period, you notice it's just all over the place. For quite a few periods for iron-rich stars, but for iron-poor stars, it's down lower, except there is this surprising 500 to 600 day period where it goes up. The story is different if there's the presence of a stellar companion. Planets with stellar companions seem to have higher iron abundance. Again, here I show that that's fairly strong statistically. Rebecca Nelson also found that, well, after several people found that there's not as much of a pileup in the Kepler field, it's been found that for iron-rich stars, that there is a pileup, perhaps not as strong, and perhaps that has to do with stars in the Kepler field being lower. So, and an important question is to, if planets are polluting their stars, do you have any, is there any signature of this that correlates with the strength of what's been called the surface mixing layer, rather than saying the convective zone? Murray and Chaboyer in 2002, they said that whatever what is ever is the mass of whatever the top layer the planets would mix in. Now, for most stars, that would be the surface convection layer until you get to stars, to higher mass stars where there is no convection zone, and so the surface mixing layer would be lower. And they found already that there seems to be a bit of a lower cutoff. So I just wanted to point out that these statistics are only possible with us all working together, and I'm glad to help contribute to finding these planets and confirming them and finding their parameters. And just for several conclusions, that a planet flow is to provide the shortest period planets, that it's not too high, it could be provided. And there's quite a bit of a difference between iron-rich and iron-poor stars. There's quite a bit of future work to do, especially to watch for period decreases. And also to quantify all that's happening, and that's why I derived these formulas and will be publishing the results from those formulas. So with these conclusions, I'll take questions.
This would be quite exciting if the flow turns out to be true. And I wonder if there's any theories of tidal dissipation in stars which depend on metallicity, because it looks like the high metallicity stars leave their planets there for a while, whereas the low metallicity stars consume them quickly and don't leave any pile.
So you're wondering whether the strength of tidal dissipation could depend on metallicity? Well, certainly the strength of tidal dissipation is not a constant, it's a function. I haven't looked at that question directly and would have to defer to theorists. Yeah, that's a good question on whether that would affect the statistics. It's not, well, I don't know if any of the theorists have any answers on that. I haven't looked for that directly.
Well, we have a theorist to volunteer.
Here's a theorist. No, I just have a comment. You saying that we could potentially measure Q for some stars of very short period planets in the next 10 years. Well, over a 10-year period. What kind of planetary periods is time for a swim? Planetary periods are you thinking of there, and what kind of planets?
Well, for example, WASP-18, I think it's somewhere around more than a 10 Jupiter mass planet in an orbit of, I remember both WASP-18 and WASP-19 are both about 1 day. I forget which is slightly more, slightly less.
Okay. So I think that's really exciting, that idea, and I hadn't thought of that before, that we could actually measure Q for some stars. So fantastic.
And one thing that's been pointed out is that the time shift increases with your time baseline squared. And some of the earlier values for the time shift were way low because they weren't taking into account of that squared factor.
So I have a question about metallicity and pollution. Is it possible to look at other indicators of stellar metallicity that can be accessed to the planets themselves? For example, the carbon to oxygen ratios, which for some extrasolar giant planets we're beginning to get, and which you can also obtain for the stars themselves. And then try to make the same sort of correlation for the carbon to oxygen ratio and the difference between them for the star versus the planet. Is that useful in trying to determine whether there's any correlation between tidal evolution and essentially polluting the stellar atmosphere with other planets? I didn't express that very well, but I think you get the sense of what I'm trying to say.
I think you're asking comparing the elemental composition of the planets versus the star.
Well, I am, but specifically with respect to this claim that there is a correlation between that.
What this actually speaks to, I meant that I've got to give a lot of praise to exoplanets.org and exoplanets.eu for compiling a lot of the statistics I used to be able to find that. And I'm not sure if there's a database a comparable database for the planets, but I admit that I tend to go for what has already been compiled, and I think that this could make a suggestion as more and more, as we have more and more transition spectroscopy results, that these measurements be put into those databases so that we could do this quickly.
Okay, on that note, I'd like to thank all the speakers this afternoon. So we can migrate to a wonder world. Thank you.